Welcome to today's session. We'll explore an interesting string manipulation problem, problem number 1297, titled Maximum Number of Occurrences of a Substring. In this problem, we'll dive into optimizing substring counts under specific constraints. Let's get started. In this problem, you're given a string S of length n and three integers, max letters, min size, and max size. Your goal is to determine the maximum number of times any substring of S occurs, provided it meets certain conditions. Specifically, the substring must have a length between min size and max size, inclusive, and contain no more than max letters distinct characters. The output is the maximum number of occurrences of such a valid substring. The input includes the string S, which can be up to 10,000 characters long, and the integers max letters, min size, and max size, all within their respective constraints. The output is a single integer that represents the highest frequency of any valid substring. This problem challenges your ability to efficiently track substrings and count their occurrences while ensuring that all conditions are satisfied. Let's look at an example to better understand the problem. Suppose the input string S is a babcab, with max letters set to 2, min size to 2, and max size to 3. We need to find all substrings of lengths 2 and 3, and check which ones meet the condition of having at most two distinct characters. For substrings of length 2, we have AA, UB, BA, BC, and CA. For substrings of length 3, we have UB, ABA, BAB, ABC, and CA. Among these, UB is the most frequent, appearing twice, and it contains only two distinct characters, which satisfies the max letters condition. Other substrings either appear less frequently or have more than two distinct characters. Therefore, the maximum occurrence is 2. Now consider another example where the input string S is AAA, with max letters set to 1, min size to 3, and max size to 3. Here, we only consider substrings of length 3, since min size equals max size. The valid substrings are AAA and another overlapping AAA. Both substrings contain only one distinct letter, which meets the max letters condition. Since AAA appears twice in total, the maximum occurrence for this example is 2. Overlapping substrings are treated as separate occurrences, which is why both instances of AAA are counted. Here's another example to illustrate a different scenario. If S is ABCDE, max letters is 2, min size is 3, and max size is 3, we again only consider substrings of length 3. The substrings here are ABC, BCD, and CDE. However, none of these substrings meet the condition of having at most two distinct characters. For instance, ABC contains three distinct letters, A, B, and C. As a result, no valid substrings exist in this case, and the maximum occurrence is 0. Finally, there are several constraints and edge cases to keep in mind. The string S can have a length of up to 10,000, and it consists of only lowercase English letters. Values for max letters range from 1 to 26, and min size and max size are bounded between 1 and the length of S. For edge cases, consider a string made entirely of a single repeated character, like AAA with max letters set to 1. Here, all substrings of valid length satisfy the conditions. On the other hand, if the string consists of all unique characters, such as ABCDEF with max letters set to 1, no substring will satisfy the max letters condition. Additionally, when min size equals max size, only substrings of that exact length are considered. If max letters equals the length of the substring, all substrings within the length bounds are valid. These constraints and edge cases highlight the importance of a robust approach to solving the problem. To solve this problem, we can start by considering the brute force approach. The intuition here is straightforward. We generate all possible substrings of the input string S that satisfy the constraints provided. Specifically, the substrings must fall within the size range of min size to max size and should contain no more than max letters unique characters. Once we have these valid substrings, we count their frequencies and determine the one that appears most often. The steps for this approach are as follows. First, generate all substrings of S within the allowed length range. Next, for each substring, check if its unique character count is within the allowed limit. If it is valid, we track its frequency using a dictionary. Finally, we return the highest frequency among all valid substrings. While this method gets the job done, its complexity is a significant drawback. Generating and checking all substrings leads to a time complexity of O(n²) where n is the length of the string and m is the average length of the substrings. Additionally, it requires n squared space to store all substrings. This makes it impractical for larger strings due to the heavy computational overhead and memory usage. To address the inefficiency of the brute force method, we can utilize a sliding window approach combined with a frequency map. The key insight here is that we don't need to consider substrings longer than min size, as they are less likely to maximize frequency under the given constraints. Instead of generating all substrings, we use a sliding window of fixed size min size to traverse the string. For each position of the window, we extract the substring and check if it contains at most max letters unique characters. If the substring is valid, we update its frequency in a dictionary. This approach is much more efficient because it avoids generating overlapping substrings multiple times. The time complexity is reduced to n asterisk min size, as we only process substrings of fixed size while traversing the string once. Space complexity is also reduced to n, as the frequency map stores only distinct substrings. This method strikes a balance between simplicity and performance, focusing on fixed-size substrings and eliminating unnecessary computations. The optimized sliding window approach builds on the insights we've discussed and offers a highly efficient solution. There are 3 key observations underlying this strategy. First, the substring length most likely to maximize frequency is min size, as larger substrings introduce additional constraints and occur less frequently. Second, the sliding window mechanism allows us to process substrings of size min size efficiently, avoiding the need to regenerate overlapping substrings. Third, by using a dictionary for frequency tracking, we ensure that only valid substrings are included, and this validation is performed in constant time for each window. This approach is chosen because it directly targets the most promising substrings, making it computationally efficient. It enforces constraints on unique characters seamlessly within the sliding window framework, achieving a balance between speed and memory usage. However, it does come with trade-offs. The method assumes that focusing on min size suffices for finding the optimal solution. While this is valid under the given constraints, it sacrifices some generality and may not extend to cases where max size length substrings are equally viable. The final complexity of this approach is straightforward and optimal for the problem's constraints. The time complexity is n, as we traverse the string once and process substrings of fixed size. The space complexity is also n, due to the storage of distinct substrings in the frequency map. This makes the optimized sliding window approach both time and space efficient, providing a robust solution that meets the problem's requirements without unnecessary overhead. In this problem, we aim to identify the most frequent substring of a given string while adhering to specific constraints. These constraints require the substring's length to fall within a given range, defined by min size and max size, and limit the number of unique characters it can contain to at most max letters. To solve this, we can start with a brute force approach, which involves several steps. First, we validate the input and initialize the necessary variables. This includes preparing a dictionary, substring_count, to store the frequency of valid substrings and a variable, max_frequency, to track the highest frequency encountered. Then, we systematically generate all possible substrings of the input string. By using a nested loop, we iterate through the string, extracting substrings whose lengths fall within the specified range. This forms the foundation of our brute force solution, which ensures that no potential substring is overlooked. Once we have generated a substring, the next step is to validate it. To do this, we check whether the substring contains at most max letters unique characters. Using a set to track unique characters in the substring makes this check efficient. If the substring doesn't meet this criterion, we skip further processing for it. However, if the substring is valid, we then update its frequency in the substring_count dictionary. Each valid substring's count is increment, and we compare its frequency to the current max_frequency, updating the latter if the substring's frequency is higher. Finally, after processing all substrings, the result is simply the value of max_frequency, which represents the highest frequency of any valid substring. To better understand the approach, let's consider some key insights. By carefully controlling the range of the inner loop, we ensure that only substrings within the allowed length range are considered. For efficient validation, we use as set to count unique characters, which simplifies the process of checking the max letters constraint.
Moreover, this brute force approach opens the door to potential optimizations.
For instance, instead of generating all substrings naively, we could use a sliding window technique to reduce redundant calculations.
In terms of data structures, a dictionary is ideal for storing substring frequencies because it allows fast lookups and updates.
Similarly, a set is perfect for counting unique characters, as it handles duplicates automatically and provides constant time membership checks. Now let's analyze the complexity of this approach. The time complexity arises from generating substrings, which involves two nested loops, making it O(n squared, and validating each substring, which takes O(k) time where k is the substring length. Overall, this results in a time complexity of O(n squared *k, where k is bounded by max size. As for space complexity, storing the frequencies of unique substrings in a dictionary requires O(m) space, where m is the number of unique valid substrings. The set used for validation requires O(k) space, leading to an overall space complexity of O(m plus k). To optimize this, we can use a sliding window approach, which avoids redundant calculations by maintaining a running frequency count of characters within the current window. Additionally, we can implement early exits, skipping further processing as soon as a substring fails the max letters constraint.
Let's walk through an example to solidify our understanding.
Suppose the input string is s equals appcap, with min size equals 2, max size equals 3, and max letters equals 2.
We start by initializing substring underscore count as an empty dictionary and max underscore frequency as 0.
As we generate substrings, the first valid substring is ab, which has two unique characters.
We increment its frequency in the dictionary and update max underscore frequency to 1.
Next, we encounter the substring ABC, which is invalid because it contains three unique characters, exceeding the max letters constraint.
Continuing this process, we find that the substring ab appears again, increasing its frequency to 2 and updating max underscore frequency to 2.
At the end of the execution, the result is the highest frequency, which is 2, corresponding to the substring ab. This Python solution efficiently solves the problem by using a sliding window approach combined with a dictionary to count valid substrings.
Let's break it down step by step. First, we import the counter class from the collections module. This allows us to count occurrences of substrings easily and efficiently. We define the method maxFrequency within the solution class. The method takes 4 inputs: the string s, max letters, the maximum number of unique characters allowed in a substring, min size, the minimum size of substrings to consider, and max size, the maximum size of substrings to consider. However, note that we only focus on substrings of length min size to maintain efficiency, as any substring longer than min size would include all substrings of length min size.
We initialize an empty counter object called substring underscore count to keep track of the frequency of valid substrings. Next, we use a sliding window approach to iterate over all possible substrings of length min size in the input string s. The range of the loop ensures that we only consider substrings within the bounds of the string. For each substring, we first check if it satisfies the max letters constraint by converting the substring into a set and checking the length of the set, which represents the number of unique characters in the substring. If the number of unique characters is less than or equal to max letters, we increment the count of this substring in the substring underscore count dictionary. Finally, after processing all substrings, we return the maximum value from substring underscore count using the max function. If no valid substrings were found, we return 0 by specifying default equals 0 in the max function. This implementation is efficient because it avoids generating substrings longer than min size and uses hashing to count substrings and check constraints. The solution is well suited for the problem's constraints and ensures correctness by adhering strictly to the requirements. Here, we begin by importing the necessary libraries and defining the solution class. The main method, maxFrequency, takes 4 parameters: the string s, the integer max letters which specifies the maximum number of unique characters allowed in a substring, and the integers min size and max size which define the range of valid substring lengths. Inside the method, we declare a map called substringCount to keep track of the frequency of valid substrings. Next, we use a for loop with a sliding window approach to iterate over all substrings of length min size in the input string s. For each starting index I, we extract a substring of length min size using s.substring, I plus min size. Then, we check whether the substring satisfies the constraint on the maximum number of unique letters, which is handled by the helper method, is valid. If the substring passes the check, we update its count in the map by either incrementing the existing value or initializing it to 1. Finally, after processing all substrings, we return the maximum frequency of any valid substring using the max method on the values of the map, or return 0 if no valid substrings are found. The isValid helper method is defined to determine whether a substring meets the max letters constraint. This method uses a hash set to keep track of the unique characters in the substring. As we iterate over each character in the substring, we add it to the set. If at any point the size of the set exceeds max letters, we can immediately return false, as the substring is no longer valid. Otherwise, if the loop completes without exceeding the limit, we return true, indicating that the substring satisfies the constraint. This method ensures efficient validation by leveraging early exits when the condition is violated. To solve this problem, we begin by analyzing the input string s equals abcap with constraints max letters equals 2, min size equals 2, and max size equals 3. The goal is to find the most frequently occurring substring of length min size that satisfies the max letters condition. First, we initialize a dictionary, substring_count, using counter, which will help us count valid substrings. Then, we start looping through all possible substrings of length min size, which is 2 in this case. For the first substring, s0:2 equals ab, we find that it contains 2 unique letters, a, b, which satisfies the max letters condition. We increment its count in substring_count, resulting in ab1. Moving to the second substring, s1:3 equals bc, we again find 2 unique letters, b, c, meeting the condition. We update the dictionary to ab1, bc1. Next, we check the substring s2:4 equals ca dot. For the substring s2:4 equals ca, the unique letters are c, which total 2 and satisfy the max letters condition. We increment its count, and substring_count becomes ab1, bc1, ca1. Then, we analyze s3:5 equals ab, which again has 2 unique letters, a, b. This substring occurs again, so we update its count to 2, resulting in ab2, bc1, ca1. Finally, for s4:6 equals bc, the unique letters are b, c, satisfying the condition. Its count is increment to 2, and the dictionary updates to ab2, bc, 2, ca1. Once all substrings of length min size are processed, we compute the maximum frequency of valid substrings by taking the highest value in substring_count. This gives a result of 2, which becomes the output for this example. Now consider a different input where s equals aaa, with constraints max letters equals 1, min size equals 2, and max size equals 3. Again, we initialize substring_count as a counter dictionary and analyze all substrings of length min size equals 2. The first substring, s0:2 equals aa, contains only 1 unique letter, a, which satisfies max letters equals 1. We increment its count in the dictionary, resulting in aa1. For the second substring, s1:3 equals aa, the unique letters remain, a, meeting the condition. We increment its count to 2, updating the dictionary to aa2. Finally, the third substring, s2:4 equals aa, also contains only the letter a, so we increment its count again. The dictionary now becomes aa3. The maximum frequency of valid substrings is 3, which is the output for this example. Let's move to another example with s equals abcde, max letters equals 5, min size equals 3, and max size equals 3. Here, we are analyzing substrings of length min size equals 3. First, we initialize substring_count as a counter. The first substring, s0:3 equals abc, contains 3 unique letters, a, b, c, which satisfy the condition max letters equals 5. We increment its count in substring_count, resulting in abc1. Next, we examine s1:4 equals bcd, which contains the unique letters b, c, d. Again, this satisfies the max letters condition, so we increment its count, and the dictionary updates to abc1, bcd1. Finally, we process the substring s2:5 equals cde. For the substring 2:5 equals CDE. The unique letters are C, D, E, which total 3 and satisfy max letters equals 5.
We increment its count, updating substring underscore count to ABC1, BCD1, CD1.
After evaluating all possible substrings of length min size, we compute the maximum frequency of valid substrings, which is the highest value in the dictionary. Here, each substring appears only once, so the maximum frequency is 1.
Therefore, the output for this example is 1.
In this problem, we are analyzing substrings of a fixed size min size from the string S, and the time complexity can be broken into distinct steps. First, the sliding window iteration involves running a loop from I equals 0 to len S min size, which means the loop executes approximately n times, where n is the length of the string.
This step contributes an O(n) complexity.
For each iteration, we extract a substring of size min size, which takes O, min size, time, as slicing requires copying that many characters. Next, we calculate the unique character count in the substring using set substring. This operation iterates over all characters in the substring, also taking O, min size, time. Finally, updating the frequency counter for the substring is an average case O(1) operation. By examining these steps, we see that the time complexity for a single iteration is dominated by O, min size, due to substring extraction and the unique character computation. When we combine all the steps, the time complexity for a single iteration becomes O, min size, for substring extraction, unique character counting, and counter updating. Since the loop runs O(n) times, the total time complexity is the product of these, resulting in O(n) asterisk min size.
Now, let's move on to the space complexity.
The primary memory usage comes from the counter dictionary, which stores frequencies of substrings of size min size. In the worst case, all substrings of this size are unique, and there are at most n min size plus 1 such substrings. Each substring requires O, min size, space to store, so the counter requires O(n) min size plus 1 asterisk min size, space in the worst case. Additionally, the set substring operation temporarily creates a set to count unique characters, requiring O, min size, space. Other variables, such as the loop indices and the substring variable, contribute only negligible constant space. As a result, the overall space complexity is dominated by the counter, which is O(n) min size plus 1 asterisk min size in the worst case. To put this into perspective, we can compare the optimized sliding window approach with a brute force approach.
A naive solution would generate all substrings of sizes between min size and max size and then check constraints for each substring.
This would involve O(n) squared substrings in the worst case, as it processes all substrings of the string. For each substring, verifying the constraints and counting occurrences would take O(l), where L is the average length of the substrings. This results in a total time complexity of O(n squared asterisk L, which is significantly worse than the optimized approach. In contrast, the sliding window method focuses only on substrings of size min size, uses a hash map for efficient frequency counting, and avoids redundant operations. This reduces the complexity to O(n asterisk min size, making it far more efficient. The sliding window approach consistently performs within the same time complexity bounds, regardless of the input. In the best-case scenario, when min size is small and most substrings are repeated, the algorithm still runs in O(n asterisk min size time. For average inputs, the runtime remains O(n asterisk min size as well. Even in the worst-case scenario, where all substrings are unique, the algorithm does not deviate from this complexity, as it always processes substrings of a fixed size min size. Mathematically, the time complexity arises because each substring operation takes O, min size, and is repeated O(n) times, leading to O(n asterisk min size. Similarly, the space complexity is dominated by the counter, which, in the worst case, requires storing all unique substrings, resulting in O(n) min size plus 1 asterisk min size space. Thus, the sliding window approach is significantly more efficient than the brute force alternative, especially when dealing with larger input sizes. When solving this problem, there are a few common pitfalls to watch out for. First, many people overlook the max letters constraint. This condition limits the number of unique characters allowed in a substring, and failing to account for it can lead to incorrect results or failing test cases. To address this, you should use a frequency map or set to dynamically track the number of unique characters in the current window.
Another mistake is implementing an inefficient sliding window.
If you forget to adjust the window size when the unique character limit is violated, you may end up performing unnecessary computations.
Always ensure that your window shrinks appropriately while still maintaining the problem's constraints.
Next, edge cases for min size and max size often trip people up. For instance, if min size equals max size or if the input string is shorter than min size, your solution needs to handle these scenarios explicitly. Lastly, brute forcing all substrings between min size and max size can result in a time complexity of n squared, or worse, which is inefficient for larger inputs. Instead, rely on sliding windows or hash maps to generate substrings more efficiently.
Another frequent issue to consider is ignoring duplicate substrings.
If you forget to account for duplicates, you might end up overcounting the frequency of certain substrings. To prevent this, use a dictionary to store substrings and their counts. Now, from an interview perspective, this problem is a great way to demonstrate your mastery of the sliding window technique. Sliding windows allow you to optimize string operations and explain why this approach is significantly faster than brute force. Additionally, your ability to use hash maps or frequency arrays to dynamically track constraints, such as unique character limits, is key to solving this efficiently. Interviewers often want to hear about trade-offs, so be prepared to compare the time and space complexity of brute force versus optimized methods, and explain why the sliding window approach becomes essential when constraints are large.
Finally, don't forget about edge cases.
Being able to articulate how your solution handles scenarios like very short strings, no valid substrings, or extreme constraints shows attention to detail and robustness in your approach. This problem is also closely related to several other classic substring challenges, which can help deepen your understanding of string manipulation. For instance, LeetCode 3, longest substring without repeating characters, focuses on finding the longest substring with no duplicate characters. Similarly, LeetCode 159 and 340 both deal with limiting the number of distinct characters in a substring, with 159 capping it at 2 and 340 allowing for a variable number, k. Additionally, LeetCode 395 flips the focus, requiring substrings to have at least k repeating characters. Studying these related problems can help you see common patterns and techniques, such as how to leverage sliding windows or hash maps effectively. They also highlight how constraints like character uniqueness, repetition, and substring length can be adapted to different problem variations, allowing you to build a versatile toolkit for solving substring problems in general. When considering alternative approaches to this problem, each comes with its own trade-offs. The brute force method, for instance, is straightforward to implement but highly inefficient for large strings, as its time complexity can range from n squared to n cubed. This approach is generally only suitable for smaller strings or when you're exploring the problem constraints. A more optimal solution involves using a sliding window in combination with a hash map. This method achieves a time complexity of n, making it well suited for larger strings and constraints, though it does require additional space to store the hash map. Another advanced technique is the rolling hash, which speeds up substring comparisons by hashing substrings dynamically. While this reduces comparison time, it introduces extra complexity in implementation, making it more appropriate for scenarios where substring uniqueness checks are critical. By understanding the strengths and weaknesses of these approaches, you can choose the one that best fits the problem's size and constraints while tailoring your implementation to the specific requirements.
Great job!
Today, we covered an efficient approach to solving the maximum number of occurrences of a substring problem. We use sliding windows and hash maps to optimize our solution. Keep practicing similar problems, and don't forget to like, share, and subscribe for more coding insights.
See you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!